Welcome back to our geometry series. Today we're up to section 6.3 where we'll be looking at arcs, chords, and central angles. Here we have our good friend circle O. Let's add 2 points A and B on the circle. If we connect them, we get a chord like we learned from last time. But let's focus on the area of the circle between A and B. This is what we call an arc. Circles can be separated into parts called arcs. When the endpoints of an arc are also the endpoints of a diameter, then the arc is called a semicircle. It's one half of the circle. We can use this notation for arcs. Instead of having a straight line for a segment, we have a curved line. So arc AB can be written like this. Sometimes you'll need to use 3 letters to denote exactly which part of the circle you're talking about. Here, we would use ABC to denote the arc starting at A, going through B, and going over to C. If we just said arc AC, we don't really know which way around the circle we're going. Arcs are measured in degrees, just like an angle. The measurement of a semicircle is 180 degrees. Arcs smaller than 180 are called minor arcs, while arcs larger than 180 are called major arcs. So for example, arc AB is a minor arc. Major arcs must be defined by 3 points to differentiate them from a minor arc in the same circle. For example, we can use 2 letters here because we're talking about a minor arc. We would need to use 3 letters to differentiate from the major arc, ACB, in that order going around the circle. An angle is a central angle of a circle if its vertex is the center of the circle. The measure of the minor arc is the measurement of the central angle. So here we've connected the center of the circle to B and the center of the circle to C and created an angle, angle BOC. If we were to measure that, we could say that was 85 degrees. The measurement of arc BC would also be 85 degrees. 2 arcs of a circle are adjacent non-overlapping arcs if they have exactly 1 point in common. Arc AB and arc BC are adjacent non-overlapping arcs. And this leads to postulate 18. The measure of an arc formed by 2 adjacent non-overlapping arcs is the sum of the measures of those 2 arcs, which makes sense. So the measurement of arc AB and the measurement of arc BC would equal the measurement of arc ABC. Now let's take a look at this example. We have points A, B, and C along the circle, and we've connected a radius from OA, OB, and OC. Let's use the theorem 70. In the same circle, for congruent circles, 2 minor arcs are congruent if and only if their central angles are congruent. So if angle AOB is congruent to angle BOC, then the arc AB must be congruent to arc BC. Theorem 71. In the same circle, or congruent circles, 2 minor arcs are congruent if and only if their chords are congruent. So if chord AB is congruent to chord BC, then arc AB must be congruent to arc BC. And looking at the picture, you can see why this makes sense. Let's add another point D at the top of the circle. And we'll connect D to B, creating a diameter segment DB. Next, we're going to connect A to C to create a chord. Finally, we're going to state that DB is perpendicular to AC. And that leads to theorem 72. If a diameter is perpendicular to a chord, which we have here, then it bisects the chord and its arc. So if we add point X here at the intersection, we know that AX must be congruent to XC, and arc AB must be congruent to arc BC. In this example, we've placed 4 points around the circle, A, B, C, and D. Next, I'm showing a dashed line to denote the distance from the center of the circle to the chord. And that leads to theorem 73. two chords are equidistant from the center of a circle if and only if they are congruent. So if we add these points, we can say if OX is equal to OY, so if their measurements are the same, then AB must be congruent to CD. Now let's shift this one chord in a little bit. That leads us to theorem 74. If two chords are unequal in length, then the longer chord is closer to the center of the circle, which kind of makes sense. You can have a longer segment the closer you are to the center. Theorem 75. If two chords are not equidistant from the center of the circle, then the longer chord is closer to the center of the circle, which is kind of the inverse of what we just saw. Let's jump over to the whiteboard and do some examples. Okay, we're going to try drawing a circle. We know how good I am at that. That's a nice, big, happy circle. That's not bad. The center is roughly there. I'm going to draw two diameters. Let's see if I can actually get through the center of the circle. There's a diameter, and we'll try to do one kind of flat through the center. It's not looking too bad so far. And I'm going to draw a radius from the center. I'll try to do straight up. Now we need some fun points here. This is going to be A, and B is this diameter right here. And then we'll have C and D, the other diameter. The center is O, and at the top we have X. And I'm going to make a little statement over here. We're going to say that XO is perpendicular to CD. So XO is perpendicular to this diameter. So we're just going to put the little thing in here so we remember. And one final statement. The measurement of arc AC, I'm going to exaggerate this curve, so I know we're not talking about the segment AC, the chord that we didn't draw, but the arc. The measurement AC is equal to 20 degrees. So from here to here, I'm just going to put a little 20 degrees right there. So I'm going to jump over here and try to stay on the screen, and we want to list as many minor arcs that we can. How many minor arcs are in this circle? Well, let's start with the obvious ones. Now remember, a minor arc is any arc less than 180 degrees. Well, we've been given one of them right here. So this is AC over here. So arc AC, that's one of them. And just looking at this one, that's also a minor arc. Now, because this arc is 20, we know that this angle must also be 20, right? And because we have two intersecting lines, we know that this angle is 20. Opposite angles are congruent. So that's how we know that this over here is also 20, this arc measurement. So dB, yep, it is 20. Right, we have XD right here. We know this is 90 degrees here. So you know that this arc also has to be 90 degrees, which is less than 180. So we know that XD is a minor arc. And since XO is perpendicular to DC, CD, like we said, we know that this angle over here is also 90 from X to C. So XC is a minor arc. Now I can see at least 4 more minor arcs. Do you see them in the circle here? What about BC? This big guy right here. We know from C to D is 180 because we know that this is a diameter. So this is 180. Anything smaller than it must be less than that. So if this is 20, from C to B must be 160. So CB is a minor arc. And the one on the other side, so AD, this is a minor arc as well, AD. Since we have 90 degrees between X and C, we know that we have from X to A 70 degrees. And let's kind of write that in here, 70. So XA is another minor arc. And since we have 90 right here and 20 right here, that's 111, 110, I can do math, 110. XB is also a minor arc. So there's 8 minor arcs in this circle. So I'm going to write down some arcs over here, and we're going to find the measurements of all those arcs. So we want to find the measurements of DB, XD, BX, AX and XAB. Okay, so these are all measurements. Measurement, 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 measurement. And I'm still on the screen. That's good. Equals, 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 equals. All right, so dB. Where's dB? dB is over here. We already found it. It's 20 because this is 20, which makes the angle 20, which means this angle is 20, which means this arc is 20. Okay, so that was easy enough. 20 degrees. XD. XD. Well, because these are perpendicular, XD, the angle here is 90, so the arc here must be 90. That's easy enough. BX. Where's BX? BX. So from B all the way to X. So we know that when we have non-overlapping adjacent arcs, you just add them together. So we have 90 here and 20 here. So there's that math I couldn't do earlier. 110. AX is from here to here, which we already figured out because this was 90, right? And this was 20. So the remainder must be 70. And we kind of wrote that in there already. 70 degrees. And XAB. So from X to A all the way over to B. Well, let's just add that up. X to A is 70, right? And so let's just write this down. We'll do it down here because I got a little bit of room. XAB arc is 70, which is this one. A to C is 20. And from C to B would be this 180, because DC is a diameter, minus 20. So it's 160. This is a B, I promise. So 70 plus 20 plus this is 250. 250 degrees. All right, let's clean this off and do one more example. All right, unfortunately, I need to draw another circle again. I'm going to give myself a little room and put it off to the side. Circle. That's not too bad. Okay, here's a center. And what we're going to do is draw a chord across the top. This is going to be point A and B. Let's actually connect it. There we go. And then a bigger chord. We're just going to kind of eyeball it. C and D. Not sure what happened here. We'll kind of fill that in. And then what we're going to do is connect this. So it's perpendicular. And this is X. And connect this. So it's perpendicular. And this is Y. And of course, good old O. We're going to say that CD, so the measurement of CD is 30. And OX is equal to 24. So I'm just going to write that in there right now. This is 24, and CD is 30. So this whole length is 30. Well, we know this is a perpendicular to this chord, so it bisects that. So we know that this must be 15, and this must be 15. If CD is 30, then this perpendicular point from the center is going to bisect this chord. That's 5. And last, we're going to say the radius of this circle is 25. So the question is, what is the measurement of OY? What is the length from here to here? So the tricky part about this one is this last thing that we just said, the radius is 25. So what we can do is connect O to D, like this, OD, like the dog, and put 25. And we've made ourselves a nice little right triangle here. So we know that this leg squared plus this leg squared will equal this leg squared. So OD squared is going to equal OY squared plus YD squared. So OD is 25. So 25 squared is equal to OY, the thing we're trying to find. OY, we'll put parentheses on it, squared, plus YD squared. So 15 squared. This is 625. And we'll just write OY squared again, plus 225. If we subtract 225 from both sides, we get 400 equals OY squared. If we take the square root of both sides, you can find out that OY is equal to 20. 20 times 20 is 400. So here we go. And finally, between these two chords, CD and AB, which one is longer? And we can use Theorem 75. If two chords of a circle are not equidistant from the center, which they are, 20 and 24, then the longer chord is nearer the center of the circle. So since this one is nearer, this must be the longer chord. So CD is longer than AB. That's it for today. A pretty short section, but we'll see you next time.